2-1. Please charge your share your. No, I can see. My name is yeah. No, please no.
Want me to share the presentation?
Okay, share please.
Okay, wait a minute.
Okay.
Um, okay, can you see my presentation?
No. Okay. Now yes. Now yes. Okay. Please start.
Okay,
You
hello
have
everyone.
15.
Uh,
You have 15 minutes.
yeah,
Last question eventually. Okay. Thank you.
okay. Okay, today I will present our paper titled a high throughput real-time object counting framework for industrial conveyors. To begin with, conveyor counting is a practical but important task in industrial production. Accurate counting supports inventory control, production monitoring, and quality management. However, manual counting is slow and error-prone. Moreover, simple photoelectric sensor can fail when certain paths touch or overlap. Therefore, our role is to build a vision-based counting framework that can handle speed, dust, variation, and latency at the same time. The main problem is that high detection accuracy does not ultimately mean correct counting. A detector evaluates subject frame by frame, but counting is a temporal decision. In other words, the system must preserve subject identity over time. If a failed positive flicker for a few frames, it may become a failed count. Similarly, if the checker loosens subject near the counting line, the final count may be wrong, even the bounding box look good. To address that, we design the solution at the system level rather than only changing the detector. The framework has four main components. First, we have YOLO version 11 Nano EU as a lightweight detector. Second, ByCheck EU for lightweight ID association. Third, a spatial temporal filter validates subject lifespan and line crossing. Finally, asynchronous processing decouple frame capture from inference, which have reduced I/O bottlenecks in stale frames. Now I will explain the asynchronous pipeline. In the traditional pipeline, the camera capture and inference may run sequentially so the system can accumulate all frames. In our design, thread 1 constantly reads from the camera stream, while the shared memory buffer store the latest frame. The queue size is set to 1, so the system prioritizes the newest frame instead of processing stale frames. Then, thread to take the latest frame and perform detection, checking, and filtering. Next, we use YOLO version 11 Nano because it's a lightweight and suitable for real-time deployment. In our comparison, the model keeps the same metric as YOLO version 8 Nano, but use fewer parameters in a chip higher recall. Additionally, the chain is set up easy for the conveyor environment. HHV jitter simulate lighting change, dodge, and sensor noise. Translation and scaling model, small positional shift on the belt. The spatial temporal consistency framework is the main pole processing logic. It has three It has three parts. First, the temporal lifespan filter keeps only objects that persist for at least 3 frames, so short-lived noise is removed. Second, the vector-based crossing logic counts only objects who centrally cross the counting line in the correct forward direction. They have avoid double counting or invalid reserve movement. Third, EMA smoothing stabilize detection coordinates since reduce jitter near the counting line. For evaluation, we focus on final counting quality, not only object detection. Each sequence contains 5,000 frames in the round truth counts them manually annotated. The reported representative conditions include easy, medium, and hard sequences. We use three counting metrics: ACA or average counting accuracy, where higher is better; MAE is the average absolute counting error; and RMSE, which penalize larger counting errors more strongly. The report method improved the reported average counting accuracy from 94.3% to 95.9%. In addition, MAE decreased from 11.7 to 8.3, and RMSE decreased from 20.2 to 40.4. This means that the system does not only improve the average count but also reduce larger counting errors. However, the improvement is not uniform across zone sequences. Sequence A and sequence C already reach 100% input method, while the main range comes from sequence B, where the temporal logic has recovered check-in losses during high speed during high speed motion. The application study show which component contribute to the final performance. The largest improvement come from robust chaining, which increased ACA from 85% to 94.3%. Then the lifespan filter adds a small improvement to 95%. Finally, with the with the crossing logic in the full system to 95.5%. So the key message is that robust detection handle more environmental failure, while the spatial temporal logic provide the final correction for counting reliability. Real-time performance is also important. The latency breakdown show the preprocessing take 0.3 millisecond. The model inference take 3.9 millisecond and check-in plus counting logic take 0.5 millisecond. The total measured sequential latency is 4.7 milliseconds per frame. Importantly, the report is approximately 256 FPS refer to inference limited. Asynchronous throughput beyond the 3.9 millisecond inference time. Finally, this screenshot shows social life Sherman factory deployment example. The environment include dirt heavy air, more motor vibration, and non-uniform lighting. The target object are 50 kilogram salmon set moving on a high-speed conveyor belt. In this example, the system maintains stable IDs such as ID 55 and ID 56, and the accumulated count is shown at 40. Overall, the work suggests that combining lightweight detection, asynchronous processing, and temporal validation can support practical real-time conveyor counting under industrial conditions. Okay, that concludes my presentation. Thank you for your attention. I would be happy to take your questions.
Okay. Are there any questions or
Okay.
remarks? Are there any questions or remarks? No. If not,
Okay.
well, you can. The second one is who's speaking about Sakon Merkuzovic and Ulrich Jan. I don't know. Bidirectional GRU neural network for simultaneous human activity recognition. The localization using Wi-Fi, CI signal. Okay, can you, Anuchit, could you share your slide, please?
Yeah, sure.
Thank you. You have 15 minutes. I have this problem. It is a Control C, Control K. No, I don't know how to use it because I used to make. Okay. So. And now, which one is your pen drive? I think you can just. Please. See you. We don't see anything. Anuchit, are you there? Please share your stuff. Please share your stuff. Could you hear me?
Yes, please give me a second.
Your stuff whenever you can. Sorry, he called me the other day.
Please give me a moment. I have a problem with screen sharing.
Look, you have to do it. I already shared my window. You should do it in some way. I shared the window already for the speaker before. So please. Please share your stuff. Because of the computer, it's a problem. So tell me which one is yours.
It says presentation in ICCSA. Is there presentation ICCSA award? Presentation.
Because that's mine, so.
Yes, here.
One.
Yes.
So I'm deleting it. Let your file. Thank you. Anuchit, have you got problems?
Yes, please give me 5 minutes.
Okay. Even though it's a bit, well, you can start. I close my phone because it appears to be noisy.
Okay, so good morning, everyone. Thank you for joining this session. My name is Anushit Jiparaku from the Intelligent and Nonlinear Dynamic Innovation Research Center at King's Mongkut University of Technology, North Bangkok, Thailand. Today, I will present our work bidirectional GRU neural network for simultaneous human activity recognition and localization using Wi-Fi CSI signals. Co-authored with Sakhon Savanish from University of Payao. Let me start with a quick summary. We propose this unified deep learning framework that performs human activity recognition and indoor positioning at the same time, using Wi-Fi channel state information processed by bidirectional GRU network. We elevated our approach on the VARL UIT dataset, the first publicly released CESI dataset with wireless timing synchronization. Across 1,500 samples spanning 6 activity locations combinations, our bi-GRU model has achieved 98.33% accuracy and F1 score, with the lowest loss of 0.086 among all the models we tested. Why do we need to solve activity and localization together? Context-aware systems need to know both what a person is doing and where they are at the same time. Running two separate pipelines is not practical for real deployments. Think of smart homes distinguishing whether someone is seated in a living room or bedroom. Elderly care system that need to detect a fall and its location together to speed up emergency response, and intelligent building that require joint spatial and behavioral awareness for context-aware computing. Before explaining our approach, let's look at why we chose Wi-Fi. Traditional sensing methods each have drawbacks. Wearables require users to wear a device, which is impractical for continuous passive monitoring. Camera systems raise serious privacy concerns, especially in homes or care facilities. And dedicated infrastructure such as infrared sensors or pressure mats is expensive to install and doesn't scale well. Wi-Fi based sensing, on the other hand, leverages infrastructures that already exist, works non-invasively, and inherently preserves privacy. So why specifically channel state information or CSI? As Wi-Fi signals travel through a space, they reflect off objects and people, causing multi-path fading. CSI captures these changes with highly precise amplitude and phase measurements across many subcarriers. This is far richer than the traditional received signal strength indicator or RSSI, which only gives a single scalar value per measurement, not enough to distinguish subtle differences in activity or location. While Wi-Fi based activity recognition and Wi-Fi based localization have each progressed well on their own, combining two tasks remains largely unexplored. The core challenge is that we need to extract two different types of features from the same CSI measurement: activity-specific patterns that generalize across locations and location-specific cues that stay stable across different activities. Handcrafted features have proven insufficient for this joint problem, which is why we turn this deep learning. It can autonomously learn hierarchical representation directly from raw signals. Looking at related work, early studies showed it was feasible to detect human presence just from Wi-Fi signal fluctuations. More advanced models use CSI to detect the multi-path distortion caused by movement, enabling recognition of activities like walking, sitting, and falling. Deep learning architectures, CNNs and RNNs, automatically extract spatial, temporal features and improve accuracy over handcrafted methods. Bidirectional LSTM networks in particular excel at modeling complex temporal dependencies, and comparative studies show bi-LSTM consistently outperforming CNN plus GRU combinations for long-term temporal structure. On the localization side, Wi-Fi has emerged as long GPS alternatives for indoor enclosed spaces. CSI enables centimeter level accuracy by fine-grained phase and amplitude data that RSSI model methods simply don't have access to. The main approaches are fingerprinting, which compares observed signal to a pre-built radio map, geometric methods like trilateration and angle of arrival, and deep learning, where CNNs learn direct mappings to spatial coordinates, and LSTMs model temporal dependency in dynamic environments. Now let me walk through our proposed framework. It has four sequential stages. First, data acquisition, where we capture raw CSI using USRP, software-defined radios as three spatial positions, left, mid, and right. Second, data pre-processing, where raw CSI is extracted, sanitized, and normalized. Third, classification, where our BiGRU model processes our pre-processed sample. And fourth, evaluation, where we measure accuracy, precision, recall, F1 score, and examine confusion metrics. Let's go through each stage. For data acquisition, we use software-defined radio platform with USRP B200 mini devices to capture raw Wi-Fi CSI as volunteers perform activities at different spatial positions. Specifically, we use two USRP B200 mini devices with VERT 2450 Wi-Fi and initial running to GNU radio, implementing the IEEE 802.11 protocol. We evaluate on the YARL UIT dataset introduced by Tan and colleagues. It is first publicly available Wi-Fi CSI dataset that uses wireless timing and synchronization for the joint task, activity recognition, and indoor positioning, filling a real gap in the literature. The dataset covers two activities, hand up and to the left. Here, you can see some examples CSI amplitude signals for A6 activity location combinations. Moving to pre-processing, our pipeline has three steps. First, CSI extractions from the pilot subcarrier, splitting the signals into amplitude and phase components. Second, amplitude sanitization, applying median filter and window size 5 and removing outliers beyond 3 standard deviations. And third, normalization, min-max scaling sample to a 0 to 1 range so network trains more stably. Before describing our model, let me briefly explain the gated recurrent unit, or GRU, introduced by Shou and his colleagues. GRU addresses the vanishing gradient problem in standard INNs through gating mechanism that governs how information flows across time steps. It has two gates. Our proposed architecture extends to this idea to a bidirectional GRU or bi-GRU. It processes the input sequence in both the forward and backward directions. So why is bi-GRU a good fit for Wi-Fi CSI data specifically? We highlight four disadvantages. First, temporal depth. It captures both short and long-term dependencies in sequential CSI patterns. Second, bidirectional context. It identifies and features that depend on both presenting and subsequent signal characteristics at the same time. Third, computational efficiency. Fewer parameters than by LSTM mean faster training and reduce overfitting risk with limited data. And fourth, automatic feature extraction. The bidirectional structure reduces our reliance on manual feature engineering for this joint recognition task. For For our experiments, we use GoColab Pro Plus with Tesla V100 GPU. Here are our results. CNN1D reached 90.80% accuracy but with high variance of plus or minus 8.37%. LSTM was similar at 90% accuracy but higher variance. By LCM improved substantially with 95.67% with much lower variancy. And unit directional GNU reached 98.13%, and our proposed by GRU achieved the best result with 98.33% accuracy and F1 score with the lowest loss of 0.09. And this chart visualizes that trend clearly. As we move from simpler to more sophisticated recurrent architectures, accuracy consistently improves. Bidirectional processing gives a clear gain over unidirectional counterparts. Let's briefly unpack why each model behaves this way. CNN1D derived meaningful spatial representations but fail to properly model the temporal variations that are critical for activity classification. And its high variance indicates its stability. LCM shows high photofold variance, pointing to unreliable training behavior across different data subsets. By LCMs, by the directional context yields a notable gain on a much lower variance, confirming the value of passing signals in both temporal directions. And our BiGRU combines efficient gauging with bidirectional processing, giving the best feature representation and both stable results across all folds. This confusion matrix shows the BiGRU classification behavior across 6 classes. Nearing all the diagonal entries approach 1.00, meaning almost perfect classification. I want to highlight one key thing: the comparison between BiGRU and the unidirectional GRU. BiGRU reaches 98.33% accuracy with standard deviation of just 0.3%. The most stable result across our architecture we tested. GRU alone reaches a respectable 98.13%. To conclude, this study introduces unified framework for jointly recognizing human activities and estimating indoor positions from Wi-Fi CSI data using BiGRU networks, demonstrating that both tasks can be inferred simultaneously from the same measurements, removing the need for separate detection pipelines. Our model achieves 98.33% accuracy, surpassing CNN1D, LCM, BiLCM, and GRU baseline under identical conditions. Looking ahead, we see four directions for future work. First, the dataset expansion, including more activities, location, and wider variety of participants to assess generalizability. Second, phase integration, exploring multimodal of phase measurement alongside amplitude data to further improve recognition performance. Third, model compression, applying pruning, quantization, and knowledge distillation for real-time inference on IoT and embedded platform. And fourth, sensor fusion, combining Wi-Fi CSI with accelerometers or radar for more robust recognition in challenging multi-user environments. So thank you very much for your attention, and I will be happy to take any questions.
Thank you very much for your very nice presentation. Are there any questions or remarks? No, but everyone. So you said that you are working on this stuff. Which kind of things you already got it so far?
May I hear that?
You said future something. I'm curious. I'm Domenico Labate. I'm a mathematician, but I'm still curious because I'm working on graph theory on Wi-Fi.
So in the future, we are getting our own information for more complex procedures in the future.
Okay, that's it. So thank you very much. Bye bye. The next speaker will be one of the Brazilian guy. I guess Brazilian. So
Lucas.
he's speaking. Which one is speaking?
Lucas, can you hear me?
Yeah. You speak about metaheuristic optimized ensemble learning for are you say?
Yes, I
Yoma.
will.
Yeah. Okay.
I
So
will
you
share
can
my screen.
whatever you want. I put the microphone mute because it creates problems.
Okay, I will share my screen now.
You have 15 minutes plus any question.
Can you see my screen?
Yes.
Sure. So, hello everyone, good morning. My name is Lucas, and today I will present our work, Metaheuristic Optimized Ensemble Learning for Glioma Gradient. This work was done with Saulo Vilela, Luiz Maciel, Raul Neto, and Marcelo Vieira from the Federal University of the Juiz de Fora, Brazil. Gliomas are the most common primary tumor in the central nervous system. Accurate grade is very important because it affects treatment, prognosis, and clinical decisions. In the latest World Health Organization classification, they included molecular biomarkers which have improved glioma diagnosis. However, these tests are often expensive and take time to obtain the results. So, the machine learning methods have become a promising tool to support glioma grading using the available clinical and molecular data. So, many machine learning models has been used successfully in biomed classification. However, no single model works best for every data set. So, ensemble methods, they can improve performance, but traditionally, approach usually use fixed model combinations. So, in our work, we use particle sum optimization or PSO to automatically find the best weight for each classifier in the ensemble. So our goal in this work is focus on improve recall because reduce false negatives is very important in glioma grading and can lead to better patient outcomes. This slide summarize our proposed framework. So you use clinical and molecular features as input to 9 classical machine learning classifiers. And we first evaluate 2 conventional ensemble strategies, hard vote and soft vote. And then you propose a PSO weighted soft vote ensemble where the weight of each classifier is automatically determined by the PSO. So if finally the optimization can be driven by different objective functions, allowing us to maximize accuracy, F2 score, or HEUC, depending on the desired evaluation criteria. So we test our method using 2 public glioma datasets, is the Cancer Genome Atlas, or TCGA, and the Chinese Glioma Genome Atlas, or CGDA. Both these data sets include clinical and molecular data, and the clinical features are age and gender, and the TCGA also includes the race. Both datasets contains the mutation status of 20 glioma-related genes, and all molecular features are binary. So this means a gene is either mutated or not. And we use glioblastoma multiforme, or GBM, as the positive class in all our experiments. So here are the main characteristics of the datasets. So these are the preprocessed datasets provided by previous studies. And the TCGA dataset has 839 samples and 23 features. So these include the 3 clinical and 20 molecular features. And the TCGA dataset has 286 samples and 22 features. The only difference here is that the CGGA dataset does not include race, because all the patients are from the Chinese population. These tables also summarize the features available in TCGA dataset, and as you can see, the dataset contains a small number of clinical features, including gender, age, and race, together with 20 molecular biomarkers related to glioma. So these clinical and molecular features are used as input for all the machine learning models evaluating this study. Before training the models, we apply a pre-processing step. So first we normalize the age features using a min-max scale to the range of 0 to 1. And to avoid any data leakage, the normalization parameters were computed only using the training data and then apply it to the corresponding test fold. Next, we applied the race feature using one hot encode, and the binary molecular features remain unchanged. Finally, we did not apply any data balance or resampling, so this allows us to evaluate the proposed method on the original data distribution. So we evaluated 9 widely used machine learning classifiers, and this model was selected because they represent different learning strategies and have been successfully applied to biometric classification problems. The prediction was first evaluated individually, and later we combined them using the ensemble strategy present in this work. So before training the models, we optimize the hyperparameter using random search. So you choose this approach because it's more efficient than exhaustive grid search when you explore a large hyperparameter space. And during this process, we use the F2 score as the optimization criteria. And to obtain a reliable performance estimate, we adopt the next cross-validation strategy. So the other tenfold cross-validation was used to evaluate the models, while the inner five-fold cross-validation was used for hyperparameter tuning and model selection. So this next evaluation strategy ensures that each sample in the dataset is used for testing exactly once. So this helps prevent data leakage, reduce overfitting, and provides a more reliable estimate of the model's generalization performance. Next, we investigate 3 different ensemble strategies. So hard vote, soft vote, and the weighted soft vote. So in the hard voting, each classifier votes for a class, and then the final prediction is determined by majority vote. In soft vote, the predicted probabilities are averaged across all classifiers. In our proposed approach is the weighted soft vote ensemble. So instead of assigning the same importance to every classifier, we assign a different weight to each one. So the final prediction is then computed as the weighted average of the predicted probabilities, shown in this equation. So the key idea is that these weights are not manually defined, Instead, they are automatically optimized using PSO, allowing the ensemble to better adapt to the chosen optimization objective. So depending on the objective of the application, the optimization can maximize accuracy, F2 score, or HUC. This flexibility allows the ensemble to be adapted to different evaluation criteria. It is important to note so this slide the optimization is performed only in the training folds within the next cross-validation framework. So the optimization weights are then fixed and evaluated on the corresponding independent test fold. So this ensures a fair and unbiased performance evaluation. So now I'll present the results. So these tables present the performance of the individual machine learning models on the CGA dataset. Overall, the classifier achieved very similar performance, with the accuracy ranging from approximately 85 to 88%. And the logistic regression achieved the highest accuracy, precision, and FU score, while Adabush retained the highest recall and F2 score. In terms of HUC, the best result was achieved by KNN, and with 99% on HUC. And this result indicates that no single classifier consistently outperformed the other across all evaluation metrics, which motivates us to use an optimized ensemble approach. So in this table, we show the result obtained on the CGA dataset. Compared to the TCGA dataset, this is a more challenging classification problem, resulting in lower performance for all individual models. So Navy Base achieved the highest accuracy, precision, and HUC, while the logistic regression obtained the best recall, F1 score, and F2 score. So once again, no single classifier consistently achieved the best performance across all metrics, reinforcing the need for an optimized ensemble that can combine the strengths of different models. In this table, we show the results when we combine all 9 classifiers into one ensemble. First, we test the traditional hard vote and soft vote approach. And then we optimize the ensemble weight using the PSO with 3 different goals: accuracy, F2 score, and HUC. Overall, the PSO ensemble consistently outperformed the conventional voting strategies. The ensemble optimized for accuracy achieved the highest accuracy, while the one optimized for F2 score got the best F2 score and recall. So this showed the effectiveness of optimizing the ensemble according to the method that we want. We also test ensemble with 4 and 5 base classifier to see the impact of the ensemble size. It notes that the best overall result came from the ensemble with 5 classifiers. So the one optimized for accuracy hit the highest accuracy and F2 score. And for the ensemble with 4 classifier, the one optimized for F2 score achieved the highest recall and F2 score, while the one optimized for HUC got the best HUC. So these results show that performance depends not only the optimization goal, but also the number of classifiers you use. So in this table, we show the ensemble results on the CGA dataset using the 9 classifier. As before, we compare the traditional hard vote and soft vote methods with our PSO-based ensemble. And in this dataset, the ensemble optimized for F2 achieved the best overall result, getting the highest accuracy, recall, F1 score, and F2 score. In particular, it reached a recall of 98%. So this is very important for glioma grading because it greatly reduced the number of false negatives. So this result showed that optimizing the ensemble for F2 score can improve recall while keeping a competitive overall performance. So finally, we evaluate the ensemble composed of 4 and 5 classifiers for the CGA dataset. So in contrast to the TCGA dataset, using few classifiers did not improve the overall performance. And the best results were generally obtained when we combine all 9 classifiers. So this suggests that for the CGA dataset, a larger ensemble provides better generalization than an ensemble with less classifiers configuration. We compare our method with the state of art provided by Tassi and colleagues on the TCGA dataset. And overall, our PSO ensemble achieve competitive or even better performance across all metrics. So the ensemble optimized for accuracy got the highest accuracy in F1 score. The one optimized for F2 reached the best recall in F2 score. And the one optimized for HUC got the highest HUC. We also compare our method with the state of art on the CGA dataset. And the method by test achieved highest accuracy, precision, and HUC, but our ensemble optimized for F2 improved the recall, increased to 98.5%. As a result, it also got the highest F1 score and F2 score among all the methods we test. And these results show the advantage of this kind of optimization. So, because in clinical application, maximize recall is often more important than the accuracy because reduce false negatives, helps avoid misdiagnosis, and can improve patient outcomes. So to conclude, we propose a BCO-based weight soft volt ensemble for glioma glade using clinical and molecular data. And our results show that optimize the ensemble for different objectives such as accuracy, F2 score, and HUC improve the corresponding evaluation metric. And overall, the proposed method outperformed individual classifier and conventional both strategy on both datasets. And in particular, optimized for F2 score achieved excellent recall while maintaining competitive overall performance. For future work, we plan to evaluate the proposed framework on large and more feature-rich datasets and further investigate its robustness and generalization ability. Thank you for your attention. I will be happy to answer any questions.
Thank you very much for your very interesting talk. Are there any questions or remarks? No. Sorry. We don't have any question or remarks. But was very interesting. Bye-bye.
Okay, thank you.
Bye.